Hello guys and welcome. Today we'll be looking at bubble sort in assembly. Let's just quickly go through bubble sort so that you know what you'll be doing in the assembly. Let me take a small array. For example, let's say we have 4, 3, 2, 1. I have it reverse sorted, so since it's a small array, more steps will be run on this. I have the pseudocode with me. So here we have a function bubble sort. We don't need the function, we just need the algorithm. So we basically have two loops, outer loop, inner loop, and a comparison check. So the outer loop runs from for I, it runs from array length minus 1 to 0. And the inner loop for j, it runs from 0 to I minus 1. And the basic operation, the comparison check, it checks if the jth element is greater than j plus first element. That is, it checks in the adjacent elements if the first element is greater than the second element. If the first element is greater than the second element, perform the swap operation. So why does this work? Let's see. Let's do that. So we have 4 and 3. We check 4 and 3. So 4 is greater than 3. We swap 3, 4. Then we check from 4, 4 and 2. 4 is greater than 2. Therefore, we perform swap. We get 2 and 4 here. Then again 4 and 1. We swap 1 and here we get 4. So the array which we get after first pass is 3, 2, 1, 4. If you can't see, I'll just make it up a little. Yeah. So can you see basically what has happened here? So we have this entire array. Here the largest element that was present, that is 4, we have pushed it to the back. This is why it is called bubble sort. The largest element in the current searching array is bubbled to the end. The same thing will happen for next 3. We will not consider 4 now. We'll just consider 3 to 1. So 3 to 1 comparison. 3 is greater, swap. 3 and 1, 3 is greater, again swap. So now you can see you will get 2, 1, 3, 4. So from the array which we had 3 to 1, the largest element 3 is pushed to the end. This is why it is called bubble sort, because the largest elements is bubbled to the end. And we go on doing this by reducing the size of the array. So now you have the basic idea of the bubble sort. Let's see how you can implement that in the assembly. There are three main things for bubble sort: outer loop, inner loop, and comparison check. So for the outer loop, in normal code we use I, j, the variable name can be anything, and comparison check also we use j. But for assembly, we'll change the algorithm a bit. In the above algorithm, let me just show you. I is running from array.length minus 1 to 0. Let's say array.length is equal to length. So it's running from length minus 1 to 0. Then j is running from 0 to I minus 1. 0 to I minus 1. And we are doing comparison check between j and j plus 1. So here we are going to tweak a little bit in the inner loop and the comparison check. So what basically we'll do, instead of checking from 0 to I minus 1, we will do I to 0. It's actually the same thing. From 0 to I minus 1, and I to 0. So we'll be exiting at 0, so 0 won't be counted. So it's same as before. There will be I minus 1 operations here. And for comparison check, we'll not be using j, but a new variable called k. We'll be using registers just for convenience. I'm telling here k equal to 0. So we'll be checking for k and k plus 1. We'll be initializing k equal to 0 between outer loop and inner loop. So actually it will be inside the outer loop but before the inner loop. So that we have set the the index of the array as 0. So it points to the start of the array each time before we run the inner loop. Now one basic thing you must understand is we have various registers in 8086. So which register to use for which variable? For the outer loop, inner loop, and for indexing, that is k. The most commonly used register for like looping is CX, counter register. Then for indexing, we can use SI, source index, or DI, destination index. These are used mainly for indexing for offsets to access elements of array. So these are best used for this purpose. Then one more register that we can use is accumulator. The accumulator is basically used to store intermediate values for ALU operations. Then we have two more registers, BX and DX. For this program, we'll be using BX. Well, we could exchange BX, CX, DX with each other anyhow, it would not matter. But using CX for inner loop gives us a slight advantage in writing the code. How I will let you know. I hope I hope you have understood what all I said till now. Let's move to the code now. As you can see, this time I've not written all the code previous like already. I thought let's write the code together. So I'll be writing the code so you can understand how to approach this problem and not just by heart all the instructions. I am assuming you have seen the binary search video. Therefore, I'll be not explaining the basic stuffs. So let's just quickly get on with the code. So first we declare our model, that is model small. Then we'll declare the data section. For the data section, we'll just require two variables. One is the array, which will define byte. We can give it as 4, 3, 2, 1, same one which we used as an example. Then we'll declare a variable called length. We'll define word, how to calculate the length, offset minus address of array. So we are done with the data segment. That's all we need for this code. Let's go to the code section. The first instruction that you would like to write is move the offset of data segment into the accumulator and then initialize the data segment register with the offset address. The next instruction we are going to write is initialize the BX register, that is the outer loop variable with length. But remember, we are going to run the loop from length minus 1 to 0. Therefore, we have to decrement it by 1. After this, we'll write our outer loop. So in this, we'll use the labels. We'll write the outer label. Start by initializing the inner loop variable. So for the inner loop, we'll be using Cx. We'll initialize with the current value of Px, and then the next instruction would be to initialize the k variable, that is the index variable. So we'll be initializing it with 0. That's it. That's all we need for the outer loop. After the outer loop, we can directly declare the inner loop label. You can see here, I don't need to jump anywhere because after the outer loop, we are not going to perform any checks. Directly, we are going to go inside the inner loop. Inside the inner loop, well, before writing the code for inner loop, I would like to write the initial values for these codes so that you can know what value is going on. So here you can see that length of this array will be equal to 4. Length is equal to 4 because there are only 4 elements. Therefore, value of bx will be equal to 4. But then we are decrementing bx by 1. So therefore, the current value of bx will be 3. Then in the for outer loop, we are going to initialize cx with current value of bx, which will be 3, and si with equal to 0. From our pseudocode, you can see that there are two operations inside the inner loop. One is checking, that is comparing. One more is swapping. When are we going to swap? We are only going to swap when the first element, that is j or k, is greater than a value at k plus 1. But before swapping, we need to compare. So let's see how we are going to compare the two adjacent elements of the array. For that, I'll be storing the value of the first element into accumulator, then increment the index, and then compare with this second element. That is, we'll be using AL. AL is the lower byte of AX register. What will we move there? We'll copy the data that is present in array SI. So basically, array SI. What is the value of SI? You can see here it's 0. Therefore, 0. So the 0th element, that is the first element, is 4. 4. So we are moving this value into AL. So therefore, AL is equal to 4. Next, we will increment SI. That is, we'll increment the index. So SI was 0, now SI is 1. Now we are going to compare AL with array SI. That is, we are going to compare AL and array SI is equal to 1. What does AL store? AL store the value of array equal to 0. So therefore, we are going to check two adjacent elements here. What does the AL value, AL register hold? AL holds 4 and array SI holds, array SI is 1. Therefore, 1 means this is 0, this is 1, 3. Therefore, it is equal to 3. As you can see, the first element is greater than the second element. That is, k is greater than k plus 1. Therefore, we have to swap. Now, since the first element is greater than the second element, we will have to perform swap operation. So there are, like, if you wanted to swap in C, how would you swap? You would declare a temporary variable, store the value of first element into the temporary variable, then assign value of second element into the first element, then value of the temporary variable into the second element. Therefore, it will require 3 steps. Or else you can write a ready-made function that will do this task for you. And we just have that in assembly. Here we are going to use a new command or instruction called XCHG, that is exchange values of AL and whatever value array is holding at index SI. Let me just show it to you. So AL currently holds, what does AL currently hold? AL holds 4 and array SI holds 3. So AL holds 4 and array SI, that is array 1, equal to 3. What does the XCHG, that is the exchange command, do is it assigns AL equal to 3 and array 1 equal to 4. How does it do this? So it uses the same method as we do in C. It uses a temporary variable. That temporary variable could be any free general purpose register. As in this case, it could be the DX register, which we are not using in this program. Therefore, it could first assign the AL value in the DX, then AL equal to array SI, then array SI equal to DX. This could be what that happens inside the assembler, but you need not worry about this. It's all taken care by the assembler. All you need to do is write exchange AL array SI. That's it. But it is not going to swap the values from the first element and the second element. It's swapping the value from the register AL and the array SI. We still need to swap from the first element, that is array 0. So right now we have AL, as you can see, AL was 4 and array was 3, which is reversed now. AL is 3 and array 1 is equal to 4, and array 0 is also equal to 4, because we are not changed array 0 anywhere here. So for that, what we will do is we'll move array SI minus 1 AL. That's it. So what is array SI minus 1? Array SI minus 1 is SI is equal to 1, therefore 1 minus 1 is equal to 0. 0 is equal to 4 currently, and AL equal to 3. But we are moving AL equal to 3 into first element of array. Therefore, array of 0 will be 3. So what our array now looks like is 3, 4, 2, 1. This is 0 and first position of the array with whom we have operated till now. Now there is one thing that we are missing. What if the comparison operation gives a result that says that the first operand is not greater, that is, when we do not need to swap. All we need to do is when the first element is less, that is, if the first element is less, don't swap. So we'll do it like jump if below. From the previous video, you know that this instruction runs when the first operand is less than the second operand and the carry flag is set to 1. Where are we going to jump? We'll declare a new label, no swap. Now let's define this label, no swap. If the first operand is less than the second operand, all we need to do is move forward with the algorithm. We just don't need to perform these two instructions. Therefore, this is equivalent to skipping these two operations. As I previously discussed, there are only two operations in the inner loop. One is check comparison, one more is swapping. Both of these operations we have performed. Therefore, we need to run the inner loop once again until we run out, until the CX counter becomes 0. One way to do that would be decrement CX, then if CX is not equal to 0, jump if not 0, or if jump if not equal to equal, where are we going to jump? We are going to jump to the inner loop, that is this. Again, we are going to repeat this. A simple way to do this, that the assembly language helps us to skip 2 lines of instructions, just 1 line, would be to write loop inner. What this basically does is execute these 2 instructions. So this instruction decrements CX and checks if CX is 0. Basically, it performs the same operation as the above 2 lines. This instruction is executed as long as CX is not 0. Once CX is 0, we won't go back to the inner loop. Next, after we have completed one pass of the entire inner loop, we have to decrease the BX. Same as these 2 lines, we are going to decrease the BX, and if BX is not equal to 0, we are going to jump back to the outer loop. From here, we are going to start again. Unfortunately, we don't have an instruction like this loop inner which checks automatically for the BX register. So therefore, we have to write these 2 instructions. When BX equal to 0, this instruction is not executed. That is, when we have completed our entire outer for loop, that is when the entire array has been sorted, this instruction won't run and we'll proceed with our remaining code. After the sorting, all that remains is terminating the program. As we have seen in previous video, we move the value of 4ch into AH and call the DOS interrupt 21H, then end the program. I got a review from my last video that one of my viewers could not understand what is this interrupt, why do we move the, well, like why do we use AH and all. So I'll just go through that once. So line by line, your assembly code is being run. Somewhere you execute an instruction called int, that is interrupt, with some value. What happens is, based on the value, there are various services that are provided by the DOS. It stops the execution here, and based on this value, it performs that service. Then, depending on whether to return or not to return, if it is supposed to return, it will again continue its execution. Now, the interrupt 21H. This interrupt is basically used to stop the execution for some input output operation or file handling operation or some system calls. There are other interrupts beside 21H. But for our programs, this is the only interrupt that will be requiring. The most important thing about this interrupt is that it will check the value of AH register. As we know, we have the AX register, accumulator register, which we can divide into two, 0 to 7, 8 to 15. This is AL, this is AH. We used AL as an intermediate value holder in our program. And the interrupt 21H looks at AH to see which service to be provided. So basically interrupt 21H stops the execution of the DOS and then looks at the register AH. Based on the value that AH holds, the service will be provided. Now what we did is we have put value of 4C. H is the hexadecimal notation into AH. What does this mean? It means that this value calls for the service of termination of the program. So it basically means kill the program. I hope now you're clear with what the interrupt 21 mean and how it works. Let's see the execution of our program. Now let us see how to execute our program. So I have my DOS shell open. First we have to compile it. So MSM, I've named it as MPMC.asm. You can see we got 0 warnings and 0 errors. Next we have to link it, mpmc.obj. Again we have one warning, that is there is no stack segment since we didn't declare .stack code. It won't give any major error. To run the program, you have to do is write the program name and .exe. And as you can see, the program has run, the array has been sorted, but we don't have an output. To see the output, we are going to do debug. Inside the debug, we will use the command. Here, you need to type D and press enter. So basically the D command is the display command. It displays the contents of the memory from the current offset. So basically we didn't yet start the program. Therefore it starts from 000. Here you can see this is the first 076A is the data segment and the 0000 is the offset. Then we'll use the G command, that is go command. Basically what it does is it completely runs the program once for us. As you can see, we get the program terminated normally. Therefore, the program has run successfully. Now, in the previous D command, that is display command, if you notice on the row 3 and from the last to fourth column, I'll just display it for you. 076A 0020, or actually we'll just 16. We'll see what we'll get. Okay, we don't get from 16. Just run it from 076A 0020. So here you can see the last 4 columns. We are getting 1, 2, 3, 4. That is the sorted array. Actually, I should have shown the unsorted array first. So let me just do it once again. So we'll do the display. In the display, I can see it and the see here you can see 04030201. That is our unsorted array. One way to access that is display 076A and 0020. Now you can see we get it on the first line. Now we'll run the program. Now again we'll display 076A 0020. You can see we have an sorted array. If you want to try some other values, change the number of elements in the array, let's even try that. We'll go to the code. In the code, let's put some random values 2, 1, 7, 4, 5, 3. So we have 6 elements. We'll save it. We'll go back to our DOS shell. We'll pass quit from here. Then we have to compile again since we changed the code. MPMC.asm. Then link it mpmc.obj, debug it, display. Now in our code, what we have given, we have given 217453. We have to find this in the memory segment. So in the memory segment, 217453, you can see it's here, 74536. It's there again on 076A and offset address 20. So we'll run the program. Now the 076A 0020, we should get our sorted array. And as you can see, we get 1, 2, 3, 4, 5, 7. So we didn't have 6 in our array, therefore we get sorted 1, 2, 3, 4, 5, 7. I hope you understood how to execute this. If there are any doubts, please comment. Thank you.